All right, folks, in this video, we're going to talk about the real numbers and their properties, the real numbers and their properties. And so what I want to do is I want to start with looking at what makes a real number line or the types of numbers that make number lines and review some of the notation that we are familiar with in mathematics. When we think about numbers, some of the earliest numbers that we learn are what we call natural numbers. And those are those numbers like 1, 2, 3, 4, so on and so forth. Those are your counting numbers, the very first numbers that you learn when you're learning how to count, right? And the notation for the set of natural numbers, so all of them, even though there's an infinite number of them, is given by this type of n here. A set that's a little bit larger than the natural numbers, okay, when you get a little older, you learn that, oh, there's a number called 0. And so in addition to these natural numbers, we add 0 to that and we get whole numbers, all right? And then to expand on that, not only do we know that we have positive numbers, but we also have the opposite of all of our natural numbers. And together with our whole numbers, natural numbers, we do the opposite of those natural numbers. We come up with our integers, right? And so our integers, involve all of our whole numbers, so on and so forth. But we also take their opposites. And as you think about your number line, your opposites of your whole numbers are to the left of your origin, or not origin, but the number 0, and so on and so forth. And so now we're seeing that we get a number line that has a bunch of numbers on them. Oh, I really just skipped. Right? And so we put these arrows here to indicate that we're continuing on. Of course, this is not all of our numbers on our number line because there are definitely numbers in between all of our integers. And so some of those numbers are what we call rational numbers. And so rational numbers are numbers that can be written in the form a over b, right? And when I write it that way, it looks like a fraction, but I want you to be careful here. It's in the form a over b, where a and b are at least integers. All right, so numbers that can be written as a fraction where a and b are integers, and we have to be careful here. We have to be sure that b does not equal 0 because division by 0 is illegal. You can't do it, right? It's undefined. It's not a finite number. And so any number that can be written as a fraction is considered a rational number. Now, we can take any integer, we can take 0, we can take any natural number, and they can be written as a fraction. For instance, negative 3 is the same thing as negative 3 over 1, or it's the same thing as negative 6 over 2, right? And so all of our integers are subsets of our rational numbers, and so on and so forth. So this is why I have this diagram here. Our smallest subset of numbers is our natural numbers. Included in the natural numbers is our whole numbers when we add 0. Included in our integers are your whole numbers and your natural numbers, so on and so forth, right? So our rational numbers is the biggest set that we have here, and in it, the set of integers is included. All right. Now, rational numbers are any number that can be written as a fraction. A number like 0.25 can be written as a fraction, so that's in the set of rational numbers. A number like 0.4 repeating, that can be written as a fraction. So any number that can be written as a fraction, that's a terminating decimal. Terminating meaning it has a last decimal place. Or any repeating decimals are all rational numbers. All right. Now, once we start doing that, we start filling up our number line with a bunch more numbers, right? Because there are a lot of irrational numbers. So we start to fill in our number line. However, there is another set of numbers that aren't included or that are not already filled in on our number line, and that is our irrational numbers. These are numbers that are not rational. Okay, hence the word irrational. And so these numbers, they cannot be written as a fraction. All right, which means that they don't have a terminating decimal. Their decimals will continue forever and ever and ever. We can't write out all the digits because there's an infinite number of decimals that follow the decimal place, right? And so, are digits that follow the decimal place. And so a number like these types of numbers are usually given in their exact form. One of the most popular irrational numbers that you probably have seen over and over again is the number pi, right? Now we say that pi is approximately 3.14, and I think somebody told me it was 22/7. We don't really care about these approximations, but it makes it seem like these are rational numbers. Pi is a non-repeating, non-terminating decimal, which makes it irrational. Another irrational number is a number like e, right? That's approximately 2.718, so on and so forth. A number like, let's say the square root of 2, right? We usually leave our answers as the square root of 2 because we can't take that square root. I mean, we can take the square root. It is a real number, but the decimals will never stop, right? And so all of these numbers together create what we call our real number system, all right? And that's going to be the focus predominantly of what we're going to focus on in this course this semester. We're going to look at numbers that can be replaced in variable expressions inside of functions that are defined over the real number system. And so you want to know your real number line very well. Some notation that we want to discuss, these squiggly, and I know squiggly seems very elementary, but that is exactly what I call these, squiggly brackets. When you see the squiggly bracket, it's the symbol for a set, and it's just a collection of elements or objects. In math, or in our course, in your calculus course, you're going to predominantly look at sets of numbers. And so let's say if I wanted to write the set of numbers that are even natural numbers less than or equal to 10. And I can write those in set notation, 2, 4, 6, 8, 10, right? So it's a list of distinct objects or a collection of distinct objects. When we want to write our solution in that manner, we can use this set notation here. This E-looking symbol is the notation that we use for is a member of, right? For instance, I can say that the number 2 is an element of, all right, let me get to some of this notation up here. Well, 2 is a natural number. It is also a whole number. It also is an integer, and it is a rational number, right? So I can say that 2 is an element of N, 2 is an element of W, 2 is an element of Z, 2 is an element of Q. I can't say irrational. And in fact, I don't know if there's a symbol for irrational numbers. I know rational numbers, we use this Q here, but irrational numbers, I'm actually not sure that we have a symbol for that. But I'm just going to say, oh, Q belongs to the set of rational numbers, all right, even though it belongs to more than one set. The notation for not a member of is that E-looking symbol with a slash through it, right? So I can say like a number like pi is not an element of the rational numbers since it is irrational, right? And so if I wanted to say that, then I can use that. These are sets. These are symbols for subsets of. And so when I think about sets, I'm thinking about a collection of objects or a collection of numbers per se. And so if I wanted to think about the natural numbers are a subset, or the set of natural numbers is a subset of the set of whole numbers. And I'm just going to use a regular W here, right? Because if you look at our picture here, our natural numbers fit inside this box for our whole numbers. All right, we can do other examples. I could say that the set of rational numbers is not a subset of the set of integers, right? It's actually the opposite way. It's the other way around, right? So if I go back to my sets of numbers, my rational numbers include all of these, but there are elements in my rational numbers that are not in my set of integers. And so the rational numbers are not a subset of the integers. The integers are a subset of the rational numbers. All right, so I can just do that. All right. And so these are some examples here. I'm actually not going to go over these examples. I don't want this video to be too long, but we're going to look at this in our in-class, our face-to-face session. And so I'm going to go back to some other stuff, which we'll talk about properties of real numbers. All right. And so we have a bunch of properties that relate to addition and multiplication. In each of these, we have some formulas that, helps us see or visualize or analytically think about these properties. And so in these formulas, we have any real number A, B, and C. We have a commutative property that basically says, oh, when you're doing addition and multiplication, the order doesn't matter. All right. This is only for addition and multiplication, right? It's not for subtraction. It's not for division. So be aware of that. We also have an associative property, meaning, okay, if you have all addition or if you have all multiplication, actually you can add the numbers in any order in which you want to add them, right? So it's a little play on this, but it has some grouping symbols here. And so what we can do here is we can do this addition of B plus C first and then add that to A, or we can add A and B first and add that sum to C. That's the associative property, right? The grouping doesn't matter as long as your operations is all addition or all multiplication. Our distributive property says that, oh, if I have a single number that's multiplied by a sum of another number of two numbers, right, then we can change this to a product of the term outside with the first term in that parenthesis plus that term on the outside times the second term in that parenthesis, right? We have some identities, right? The number that you add to A in order to get the identical number as your result is 0. And with multiplication, the number that you multiply A by in order to get this same identical A as your product is going to be 1. And so the 0 is the multiplicative identity and 0 is the additive identity and 1 is the multiplicative identity, all right? Additive and multiplicative inverses are the things that you add or multiply a number by in order to get these identities here, right? And so if I want to get 0, which is our additive identity, I have to add the opposite of A to A. And in order for us to get the multiplicative identity, which is 1, I have to add or multiply A by its reciprocal, which is 1 over A. All right, or just do a division by A, all right? Some other things that'll come up periodically throughout the semester is the absolute value, right? Remember, if you want to do the absolute value of a number, a real number A, it's denoted with the bar, the vertical bars, and basically absolute value is the distance of whatever you're taking the absolute value of, that distance from 0. So all you're doing is counting the number of units a value is from 0 when you're doing the absolute value, okay? And so these are some properties of the absolute values. The absolute value of A is always greater than or equal to 0 because it is a distance. And so if I do an absolute value, and I'm just looking at a straight up, strict absolute value, that value should always be greater than or equal to 0. The absolute value of negative A is the same thing as the absolute value of A, right? They all equal A, right? Because you're just on the opposite side of 0 compared to where you would be if you were just A. Now notice this, when you don't see a symbol between two variables, there's always understood to be a multiplication, right? So notice this is multiplication. This is division. What we could do to take this absolute value, if we wanted to, is we can separate it into two separate absolute values and separated by multiplication. So the absolute value of A times B is actually the absolute value of A and the absolute value of B, right? It's the magnitude of A times the magnitude of B. Now that's for multiplication. This one here is for division. If we wanted to, we could take the absolute value completely separately and we get that right there, okay? And so we get the absolute value of A over the absolute value of B, so on and so forth. Now notice this was multiplication, this was division. Have a true or false question. Well, do you think it works for addition? I'm going to leave this for you guys to think about on your own. And if you don't know the answer, you can ask it in class. All right. And so not only do we have properties of real numbers related to absolute value, the actual numbers, the sets of numbers, and all of our properties, we're going to talk about positive integral exponents. And this integral here, sometimes they like to use these big words. Here, I'm talking about positive integer exponents. For any positive integer n, a to the n is basically a multiplied n times, okay? Where a is our base and n is our exponent. Some people like to use power. I really don't care, same thing, all right? Synonyms, right? And so if I have 3 to the third power, that just means multiply 3 times, right? Which you get 27. All right, arithmetic expressions. Some people might say arithmetic expressions. Oh well. All right, these are expressions involving a combination of numbers and ordinary operations, right? So I may have something where I might have a 3 squared minus 7 times 8 plus 14 or whatever. This is an arithmetic expression. It involves multiplication, it has exponents, subtraction, and addition, right? It doesn't involve any variables, right? You want to be able to simplify these types of expressions, and in order for you to do that, you need to use the order of operations. And so we'll review the order of operations, which is basically the hierarchy of steps or the hierarchy of actual operations that you need to take in order to simplify an expression that may look like that, right? And so a lot of people remember Pemdas, right? Please excuse my dear Aunt Sally, right? And so the P is for parentheses. Now, it's not just for parentheses because you can have any other grouping symbol. An absolute value is a grouping symbol. You could have a square bracket show up in expressions. They're not special, they're just grouping symbols. You can have the squiggly brackets. I know I just said that those were sets, but sometimes you'll see people write these squiggly brackets just to say, oh, I'm grouping these things together. All right, but that's the first thing you should look for when you're doing your operations with arithmetic expressions. Then once you take care of those, you do your exponents, so your exponential expressions, and then you do multiplication or division from left to right. So if division comes first, divide first, and then do multiplication, and vice versa. And then the last hierarchy of operations involve addition and subtraction, and you do those from left to right. And so we're going to quickly do these two examples here. We're going to simplify each expression, right? This expression involves 2 minus 3. Notice that's an absolute value of 3 minus 4 times 6, close the absolute value, right? Remember, please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction, right? So if I'm going to simplify this, all right, my first thing is to look inside of my grouping symbol. An absolute value that has some stuff in it is a grouping symbol. Within that grouping symbol, I have to think about, okay, well, which of these operations is higher on the hierarchy? I have a subtraction and I have a multiplication. Oh, the multiplication comes first. And so notice here, I'm writing down this as a step, right? I'm saying here, this is my first sentence that's given to me. Notice I put an equal sign here, right? Because you want to write logically. And I'm going to do that 4 times 6, which is 24. I still have this grouping symbol, so I need to stay working in here. The only operation within that grouping symbol here is that absolute, the subtraction. 3 minus 24 is 21. I still have this grouping symbol, even though that's the only thing that's in there. I need to do this operation here. And that is actually a positive 21 because negative 21 is 21 units from 0. Now I have a subtraction and a multiplication. There's a multiplication there. You don't have to necessarily write that symbol. And so I'm going to do this multiplication next. So that'll be a 3 minus 63, a 2 minus 63, sorry, which I get a negative 61. In this example, I have a grouping symbol, right? And so this grouping symbol I'm going to do first. 25 minus 4 is a 21. I have a division as my next highest operation. And then I have a subtraction and an addition. Well, which do I do first? Again, remember, you always do addition and subtraction from left to right if those are the only operations you have. And so since the subtraction comes first on the left, I have a negative 2 plus 2, which is 0. Okay? And there we go. Last but not least, we want to talk about algebraic expressions. Now, everything else was just with numbers, right? Now we are going to add variables. And so instead of seeing just numbers in an expression, we may have a variable, right? So something like 3x squared minus 7x plus 18 over 4x squared minus 11. Right? That's an algebraic expression. We're going to get used to seeing these things here because they're very important functions. But what we want to start with is just evaluating algebraic expressions and then simplifying algebraic expressions, right? And so evaluating just means to substitute a value in for your variable, right? So let's get used to some of this vocabulary. Some people, instead of saying substitute, some people say plug in. All right, whatever. All right, simplifying algebraic expressions involves rewriting the expression so that it doesn't involve as many operations, so on and so forth. Another definition, as you can see on the screen, says use your properties of real numbers to reduce the number of operations that are in the expression. And so we're going to look at an example where we evaluate this algebraic expression. Notice here it has multiple variables in it. And in order to evaluate, you have to substitute. So I have to give you something to substitute here, right? So we're going to let A equal -3, B equal -2, and C equals 5. When I do that, notice here, the first thing I'm writing is an equal sign. Now, we're going to substitute -3 in for A. Notice here, I put a parenthesis here. It is necessary. If you don't put a parenthesis there, you might mess up, all right? I don't need that. That doesn't have an exponent, so I didn't put that in parentheses, but you can. I mean, it doesn't matter there, but it definitely matters here. All right, b cubed. So I put my -2. Again, since that's raised to a power, I put that -2 in parentheses, and that 5 there is raised to the 4th power. So I put it in parentheses there. All right, so I've done my substitutions. Now I'm going to take care of those exponents, right? Please excuse my dear Aunt Sally. We have a bunch of parentheses here, but within the parentheses, there's no operations, right? So I'm going to go next to E, which is exponent. So I'm going to do all of my exponents. Well, -3 squared is 9. -2 cubed is -8. 5 to the 4th, oh, I think that's 625. Please forgive me if I'm incorrect. All right. Now, okay, this is a good one, right? We say we do addition and subtraction from left to right, right? Well, we have a fraction here where we have a numerator and a denominator, right? So we have a division with addition and subtraction. Well, we don't know what number we're dividing, and we can't just divide the 9 by the -8 and the -5 by the 625. We have to do these operations within the numerator and the denominator, right? I'm going to do them at the same exact time. So that's going to be a 4 divided by a 617. And guess what? We're going to leave our answer like that, and we can't simplify that any further. All right? So that is that. And that is evaluating. Notice how I'm writing this. I want your work to look like this, right? I'm not saying, oh, I put my equal signs. People love to leave this off. These are connected mathematical sentences here. And so when you write your problems, you need to write it as if someone, like your colleague, your classmate, me, is reading it, and they need to read it in a logical way, right? Notice how I did that here. I want you to get used to writing your mathematics this way, because when you review your work, you'll be able to see what you've done from step to step, right? All right, last but not least, we're going to simplify each of these algebraic expressions. Here in part A, I have -8 plus 5x over a -4. That's pretty small. I hope you can see this. All right, I have an addition in my numerator, and I have a division in my denominator. One of the things that I want you to know is that when you're dividing by a single term in your denominator, all right, now I can't combine the -8 and the 5x, right? One of them has a variable and one of them doesn't have a variable, right? I can't combine those in any kind of a way. All right, the -4 is already simplified, right? Well, this statement here says simplify. Some people will say that this is already simplified, all right? For other people, which the only thing that we can do here is I could divide both of these expressions by that -4. Notice if I divide that -8 by -4, I have to divide that 5x by a -4. I never want you to get to the point where you say, oh, these two cancel to +2, so this is 2 plus 5x, because you'll be wrong, okay? Divide both of those terms by -4 and then simplify. -8 divided by -4 is a 2. And notice this is a positive 5x divided by a -4. A positive divided by a negative is a negative. And when I add a negative, that's the same thing as subtracting. And I can write my answer like that, or you can say 5x over 4. All right, let's go to part B, which is our last example in this video here. I want to simplify this expression. All right, now this is just a bunch of stuff, right? Well, think about all of your properties that can help you reduce the number of operations. All right. One, I can use my distributive property here. That'll be a 20 minus 10x. And then here, I can distribute the negative 1/2. And notice here what I said, I distribute the negative 1/2. Because remember, subtraction is the same thing as adding the opposite, right? And so what I'm going to do is I'm going to just attach that negative to the 1/2 and do a negative 1/2 times 8x, which is a negative 4x. And a negative 1/2 times a negative 6 is a positive 3. Now I have like terms, so we're going to combine like terms. Those two are like terms. I get a negative 14x, and this term and that term are like terms, and we get a plus 20. All right, that's all for this video. I'll see you in the next video.